Good evening, everybody. I'm Rick Gehring from Naperville Astronomical Association, and this is our August 2021 Observing Fundamentals program. Tonight, we're going to spend a nice hour talking about the moon, some things you can see on it, and hopefully, we're going to find out why they're interesting. So let's go ahead and jump right in. And Jim, if you could take me out of the shot, please. So, visual astronomers like us have always had a love-hate relationship with the moon. We're delighted by it, by its fascinating topography, formed by millennia of ferocious impacts and ages of widespread volcanic activity when the Earth was geologically active. But we're plagued by it when it comes closer and closer to full, grows larger and larger in the sky, acting like a mirror that's reflecting unwanted sunlight onto our fainter targets, and acting more and more like a playground bully chasing the smaller kids out of the park. But for tonight, let's accept the fact that the moon's not going away, whether we love it or we hate it. Let's appreciate its good points and see if we can ignore its occasional bad habits. To start with, let's talk a little bit about just how big is the moon, because sometimes it tries to fool us, especially when it's close to the horizon. Everybody has seen a big orange moon sitting right along the horizon that looks absolutely huge and much bigger than it looks when it's up higher in the sky. The next time that happens, I want you to give it the thumb test, like my friend on the right side of the screen here. Just raise your thumb and cover the moon with it. Now, the moon is about a half a degree wide, and your thumb is considerably more than half a degree wide, so you won't have any trouble covering the moon with your thumb, whether it's high in the sky or right along the horizon. But while you're doing it, also take a look at how big the moon looks in relation to your thumb. And it'll be probably be about half the size of your thumb when you hold it up. Then later on that night, after the moon is up in the sky, go back out and do the same thing. And I think you'll be surprised when you find that the moon at the horizon that looked so big is exactly the same size as the moon high in the sky that looks so small. And the only real reason there's a difference is that near the horizon, like we can see in the picture on the left, the moon is near things whose size we understand. It's bigger than that building on the hill. It's bigger than the hill, for goodness sake. So we know that the moon is pretty big when it's near the horizon. When it gets farther up in the sky, there's really nothing near it to compare it to. So we lose part of our sense of how large it is. But it really doesn't change size as it goes through the sky from horizon to Venus at night. It does change size depending on where it is in its orbit. When it's closest to us, at what's called perigee, on the left-hand side of the diagram, the moon's closer and it looks bigger because it's closer. When it's farther away at apogee, it looks smaller. The time it takes light to get to us from the moon is pretty constant. It's about 1.25 seconds. The difference in its distance doesn't affect that. And the distance really doesn't change all that much. In miles, it varies from about 225,000 to 250,000 miles, which really isn't much of a difference. But despite that, we've recently come across people referring to perigee moons as supermoons because they're a little bit bigger than the average full moon. Well, as you can see from the diagram, it's not a whole lot bigger. It would be very difficult to look at any given moon and determine just from looking at it whether it's near or far away, whether it's a so-called supermoon or a so-called mini-moon, because it really only changes in size by about 4 arc minutes. It varies from about 29 to 33 arc minutes in size, which isn't all that much of a change. But if calling it a supermoon gets people to look up and pay attention to what's going on in the sky, well, I think that's a good thing. There is one time when the supermoon and micromoon label makes a difference. And that's when the moon comes directly between us and the sun and causes a solar eclipse. In a normal total eclipse, like you see in the picture on the left, where the moon is just starting to take a big bite out of the disk of the sun, you can pretty much tell just from the size of the moon's shadow that it's going to end up covering the entire sun. And indeed, it did cover the entire sun that day, and we had a nice total eclipse. However, when a total eclipse is caused by a micromoon, you have a little different situation, because the moon doesn't look quite as big as the sun looks. Even though the sun is about 400 times as big as the moon in reality, it's also just about 400 times as far away, which means that when we look at the two of them in the sky, they seem to be about the same size, except when the moon is farther away from us in its orbit, and then it looks smaller, and it's not quite big enough to cover the entire sun. So we end up with not a total eclipse, but what's called an annular eclipse. As you see on the right, there was one in Chile in 2017 that I was lucky enough to be able to go witness. And as you can see, the moon is perfectly centered on the sun, but not quite as big, and it leaves that little ring or annulus of sun uncovered around the edges. And that's kind of a neat thing to see once in a while too. So how do we look at the moon? Well, to begin with, we look at the moon just with our eyes, but there isn't all that much that we can see, honestly, without some kind of vision assistance. We can really see three things on the naked eye moon. First, we see the Maria, which are the dark areas, and Maria is the plural of the Latin word mare, which means sea or ocean. When the early astronomers were looking at the moon and saw all these dark areas, they assumed that the moon was pretty much like the Earth, and those dark areas must be water, and the light areas must be land, which is not an unreasonable assumption, although it turned out to be completely wrong. So they called all of the dark areas seas or mare. The light areas are called the highlands, because they are in fact higher elevation than the mare. And the other thing that we can see naked eye on the moon are crater rays, and we can see several sets of rays. The most prominent one comes from a crater called Tycho near the bottom of the moon, and you can see the rays that go almost literally from the bottom all the way up to the top of the moon from that crater. Now, if those dark areas aren't actually seas, well, what are they? What they are is areas where, while the moon and the rest of the solar system was being formed, there was a lot of big stuff flying around loose, and it had a bad habit of running into things, like the moon and like Earth for that matter. The areas that we now see as the Maria were areas where big chunks of material in the forming solar system slammed into the moon and left huge craters. Since the moon was geologically active then, which it is not anymore, but at that time it was active, and there was lava beneath the surface. So when there was a large impact and a crater formed, lava seeped into the crater and filled it up. All of the dark areas that you see on the moon are areas where lava seeped in from underneath the crust, filled in craters, and hardened into a very dark rock called basalt. The lighter areas on the moon are areas where large basin craters did not form during that part of the moon's development, and they remain sort of the pristine material that the moon was made of. Rays form because underneath the top surface of the moon, there is a lighter colored material. And why is that? Well, the moon, unlike Earth, has no atmosphere. Since it has no atmosphere, it's being constantly bombarded by tiny little bits of stuff that are flying through the solar system, little pieces that fell off asteroids and comets and other things are constantly running into the moon. Now on Earth, those things hit our atmosphere and the friction generates heat, and the heat usually burns them up altogether before they reach the ground. On the moon, there is no atmosphere to burn them up or even to slow them down. So the moon is constantly being bombarded by these micrometeorite impacts. And what it did was pulverized all of the rock on the top layer of the moon into a fine powder. It's called regolith. So instead of being a solid rock, it's almost like sand or flour. The regolith that is exposed to the environment on the moon is constantly, again, being hit by even more micrometeors and also by charged particles that are coming off the sun and other factors that cause it to get a little bit darker than it was to begin with. But right underneath it, there's regolith material that has not been darkened by the moon's version of weather. So when an impact happens on the moon, it dredges up material from underneath the top layer, and that light-colored material is what gets flung out from the center of the crater and forms the rays. And that's why the rays that we see on the moon are light-colored rather than dark-colored. Over the years, people have made all kinds of pictures on the moon using the dark Maria and the light Highlands. Everybody knows the man in the moon, but there's a few others that you might want to look for the next time the moon is full and you have a look at the moon. In addition to the man in the moon, did you know there's a toad in the moon? He sits over there on the left-hand side, toad or a frog. There are several rabbits in the moon. This one is my favorite because of I like the little cottontail at the end and the big ears coming up, plus the fact that this particular rabbit takes up almost all of the moon's surface. So he's a guy to look for. My old friend Joe Cool lives on the moon with his sunglasses looking up. He's always looking up since he's on the moon. And finally, one of my favorites is Lucy Van Pelt from the Peanuts comic strip. I can't really draw her right, but I put her picture in there next to the moon, and you can see where one of the Maria forms her hair. You can see her eye and mouth and chin, and then down around her neck, Crater Tycho forms a diamond pendant. So we have Lucy in the sky with diamonds sitting right up there every time there's a full moon. And you can see them, and there's actually a number of other images that people have concocted in the moon. But we have the frog, the rabbit, Joe Cool, and Lucy are some of the easiest ones to see. In addition to seeing the pictures on the moon, there are a few features that you can see either naked eye or, if not naked eye, then at least with binoculars on the moon. Some of them are the major ray craters. We already talked about Tycho down near the bottom of the moon, and that nice long ray that comes up from Tycho, crosses one of the mare near the center of the moon, and it's called the Bessel ray because it passes near a crater called Bessel. There's some dispute whether that actually comes from Tycho. I can't really see any place else that it's likely to come from, though. So as far as I'm concerned, that's part of the Tycho ray system. And that would mean that Tycho threw material more than 1,500 kilometers when it struck the moon, and that's a pretty impressive throw. Other ray systems on the moon, we have two of them up near the top, Anaxagoras on the left and Thales on the right, where you can see the ray systems sort of on the top of the moon's head. We have two near the center, Copernicus and Kepler, which are both remarkable craters. We're going to see them a little later, but they have nice, easily visible ray systems. Over at the lower right, there are another pair of ray systems that would be so amazing if the moon faced a little differently. But as it is, they're kind of hidden in the corner from craters called Stevinus A and Furnarius A. And there's one called Proclus that's worth looking for. And here's why. Let's go back for a minute to Tycho. And you see on Tycho, we have rays going out to the south, to the southwest. We have rays going to the southeast, to the east, to the northeast. We have the Bessel ray going up north, and we even have one going northwest, but we don't have any rays from Tycho going directly to the west. In other words, the direction that the yellow line that I've added comes from. There's no rays going that way, and that tells us that when the Tycho impact happened, whatever hit the moon to cause Tycho was coming from the west, from the direction of that yellow line, because when an impact isn't straight up and down, the one direction it cannot throw material is backwards. So Tycho, we have a so-called zone of avoidance where there are no rays pointing to the west. In Proclus, we have an even more pronounced zone of avoidance that you can see pretty well in this view. The dark view where there's no rays, and then you can see the arrow of where the Proclus rays begin. So in addition to the ray craters, there are a few other naked eye or binocular features that you can look for, particularly at full moon. We had our bright areas with the ray craters, so let's look for some dark areas. And we have some craters that have filled with lava, and the lava, like everywhere else on the moon, hardened into that dark black rock. So we have Endymion up near the top, Plato that is near the top to the left of center. We come down around the left-hand side, we have a nice big dark crater called Grimaldi. And if you look at, use Grimaldi as a landmark, you can probably also manage to tease out that little dark crater called Riccioli. Besides the dark spots, there are some bright spots on the moon. The crater Aristarchus on the left is one of the bright spots. And again, this is where material from right underneath the surface has been pulled up by an impact and left on top of the darker material. So we have Aristarchus as one example. There's another example called Censorinus on the right side of the moon. And you can see a number of other bright craters splattered across the various parts of the face of the moon. Down near the bottom, we have a bright spot that's famous because it's old, called Cassini's bright spot, that was originally noticed by an Italian astronomer named Cassini in the 1600s using a very early telescope. And finally, although I don't think you'll be able to see this naked eye, you may be able to see it with binoculars, certainly in a telescope. On the left side of the moon, we have that little white spot that I've marked called Reiner Gamma. And Reiner Gamma is one of the most mysterious places on the moon, because if you look at it closely in a telescope, you'll find there's no crater there, there's no hill there, there's no disturbance of any kind there. It's just an area where the dark surface of that particular mare has a swirling white pattern that's about 40 kilometers across. The one thing we do know about Reiner Gamma is that it sits on top of one of the strongest magnetic fields on the moon. And we know of two other places on the backside of the moon that we can't see from Earth, but two other places where there are similar features also associated with strong magnetic fields. So if any of you can figure out why it is that those magnetic fields caused those swirling white patches to form on the mare above them, well, you may have a Nobel Prize waiting for you one day if you can figure that out, because so far no one's been able to. There are also mountain chains on the moon. There are really only two major ones. They run right down the middle between the two eyes of the man in the moon. One, the Caucasus, and the other is the Apennine Mountains. But they're not like mountain ranges on Earth. Here on Earth, mountain ranges happen when plates of tectonic plates run into each other and get pushed up. There are no plates moving around on the moon. On the moon, mountain ranges form from basically they're the rim of a large impact basin. This one, the Imbrium Basin. It's basically a huge crater that formed back during the early days of the moon's formation, and the edges that still stick up on the east and southeast rims of that basin form those mountains. Now, so far we've been talking about the moon when it's full, but that's only part of the time. So let's talk a little bit about the other phases of the moon. This is kind of a complicated diagram, but it's not all that complicated. The first thing that it shows us, we've got the sun on the left, and we have the Earth at the center, and then we have a ring of moons around the Earth, and they show us something very fundamental that we have to keep in mind when we're talking about the phases of the moon, and that is the moon is always half and half dark. It can't be anything other than half light and half dark. Just like on Earth, we're always, one half of the Earth is lit by the sun, the other half of the Earth is in shadow. One half is daytime, one half is nighttime. Same thing on the moon. The reason the moon looks different each night isn't because different parts or different amounts are being lit, but it's the angle that we're looking at. For example, at full moon, we have the sun to the left, Earth in the center, and the moon on the right. The sunlight goes past the Earth, lights up the face of the moon, and as we stand on the Earth looking in that direction, we see a full moon fully lit up. On the other hand, at what's called new moon, the opposite end of the month, we have the sun, then the moon, and then Earth. We stand on Earth at new moon and look up. All we can see is the dark side of the moon. We can't see any of the lit side. And so from our perspective, that's when there is no moon at all in the sky at night. In between, at the quarters, well, you see what you would expect. You see half of the moon lit and half of the moon not lit. And before the quarters, we see less than half of the moon being lit, more than half being unlit, and that's how we get that nice crescent shape before the first quarter moon. And afterwards, we see more than half lit and sort of an unlit crescent. Now you're probably wondering why it is that we can ever see a full moon, since we have the sun on the left, the Earth in the middle, the moon on the right, and the Earth's bigger than the moon. So why isn't the Earth blocking the sun and keeping it from getting to the moon? Well, the answer is that the moon orbits us at an angle. It's only about a 5-degree angle, and this is probably not a really good diagram because it's definitely not to scale. But the moon is almost always either above or below the line between the sun and the Earth. So at full moon, here we would have the moon on the right. You see the sunlight is going over the top of the Earth and lighting up the moon. And at new moon, it's underneath going under the Earth. There are 2 points, though. You can see where the yellow line of the moon's orbit crosses the dotted red line of Earth's orbit around the sun. There's 2 points, one on this side of the planet and one on the other side, where the moon's orbit and the Earth's orbit cross, and those are called nodes. If the moon is at a node while all 3 objects are lined up, we'll have an eclipse. And that's the only time we can have an eclipse, because the moon has to be centered on the Earth and the Earth has to be centered on the sun in order for the moon to block the sun if it's a solar eclipse, or in order for the moon to come within the Earth's shadow if it's a lunar eclipse. And that's why both solar eclipses and lunar eclipses don't happen very often, because it only happens if the moon happens to be at a node at that particular point in its orbit. One final thing that you can do observing the moon naked eye is to watch for young new moons. If you use a lunar calendar, the month begins right after new moon. You can see the moon is going around counterclockwise. You see new moon there on the left. And as soon as the moon gets past new, the sun is going to light up a little tiny sliver on the right side of the moon that will be visible from Earth. With a lunar calendar, that's the moment when the new month begins. And so that's an important aspect for cultures that use a lunar calendar. And for that reason, the ability to spot tiny little narrow crescent moons is one aspect of naked eye moon watching. This is a moon that's 34 hours past new. I will tell you that it would actually be very difficult for you to see this moon naked eye. Certainly nowhere near as easy as this picture makes it seem, and it's not a bad challenge if you want to give that a try. So much for naked eye. Now let's talk a little bit about what you can see on the moon in a telescope. And I'm going to do this in 2 parts. First, I'm going to talk about the general types of things that can be seen in a telescope on the moon. And then we'll take a real quick tour of some examples day by day on the moon. So let's start with what the types are. The most frequent thing that you're going to see on the moon, of course, is craters. And there's basically 2 kinds of craters. One, the simple or bowl crater, is exactly what it sounds like. Something hit the moon and it left a bowl-shaped impression in the surface of the moon, and that's about it. Bowl craters can be up to about 20 kilometers across. Anything beyond that is going to start to show some of the characteristics of what's called a complex crater. There is a complex crater in the center here, the crater Copernicus, that we saw its ray system earlier. And complex craters are definitely not like bowls. They show terracing in the walls, and you can see in Copernicus, you can see how the walls of the of the crater have formed different layers as they're kind of slumping in after they form. They form central peaks because the impactor that causes the crater hits the moon and it pushes the crust down. But after it pushes the crust down, the force that pushed it down dissipates and the crust tends to rebound back upward and it forms these central peaks. Now, to give you an idea, the most central peaks are between 1 and 2 kilometers tall. Some of them get as big as or as tall as 4 kilometers above the crater floor. Large complex craters like Copernicus can generally be 2 to 4 kilometers from the top of the crater wall down to the floor, and the distance from the top of the crater wall to the surrounding area where the undisturbed area where the crater formed can be 1 to 2 kilometers. So I wouldn't want to have to climb any of those things. One of the things that tends to happen to complex craters is the so-called floor flooding that we see in craters like Plato that we see on the right-hand side. Now, when it first formed, Plato probably looked a lot like Copernicus. It's about the same size. It definitely has terracing that you can still see in the exposed tops of its walls. And it almost certainly had 1 or more central peaks like we see in Copernicus. But after the crater formed, cracks developed in the floor of the crater, and lava seeped into it from below. In the case of Plato, it probably got to 2 or 3 kilometers deep, enough to cover up the central peaks, not enough to fill it all the way to the top. But that's an awful lot of lava. You can also see in the view of Plato, one of the nicest things about large craters and particularly flooded floor craters, they provide a wonderful backdrop for the shadows that let us trace the shape of the top of the crater wall. If you look at the right-hand side, you get a pretty graphic picture of how jagged the top of Plato's eastern wall is from the way it's throwing those shadows. So what else can we see on the moon? There are things called rills, which basically a fancy way of saying cracks in the ground. We have quite a few of them in the crater on the left, which is a crater called Posidonius. The most prominent rills in the center are probably what used to be lava tubes or lava channels, where lava flowed across the floor of the crater and left those channels to mark where it passed by. There are also some cracks, as you can see, sort of around the edges or paralleling the edge of the crater on the left, and those happen fairly frequently in larger craters and also in along the edges of mare, because the lava that's sitting in there is just immensely heavy, and the ground underneath that lava, the rock underneath the lava, tends to crack from the weight, and it sinks. And when that part of the floor sinks, these subsidence cracks happen that sort of parallel the shape of the mass of lava that's causing the cracking. In the middle, we have an example of what's called a fractured floor crater, which is in a way sort of the same process but in reverse. With a fractured floor crater, lava builds up underneath the floor of the crater, but it doesn't have a way to actually get into the crater. You can see in the example in the center, it's a crater called Terentius. You can see its central peaks are still there. It is not flooded with lava the way Plato did, or the way that Posidonius on the left did. But underneath, there was an upwelling of lava that was probably disturbed by the Terentius impact. The lava flowed up, and as it flowed up, it caused the floor of the crater to push up until it literally cracked and broke. And you can see that dark line where the floor fractured at the upper right quadrant of the floor of the crater. On the right, we have a wonderful example of a scarp, which is, again, is a fancy word for a cliff. This particular one is called Rupes recta, which is Latin for the straight wall. The British call this the railway because it's such a nice straight line. And some people like to call it Huygens sword because the long dark line there looks sort of like a 17th century sword blade, and you can see the hilt at the bottom end of the blade, and the hand guard that comes below the hilt. Scarps occur when there's a fault in the underlying material that causes two adjacent slabs of rock to shift. One shifts up, one shifts down. It looks like an awfully steep feature, although it's actually not. The straight wall itself it's only 250 to 300 meters tall, and the slope is only about 20 degrees. It looks like it's nearly vertical from here, but that's mostly due to the way the shadow is coming across. So those are scarps.
Hey Rick, you got a couple Facebook questions that came in. So one question is the moon tectonically active?
No.
It's not.
Has not been. It's the moon. I don't think the moon has ever been tectonically active with plates shifting around on top of a layer of plasma-like material like happens on Earth. Its geologic activity was volcanic, but the vast majority of its volcanic activity ended long ago, and possibly all of it ended long ago, although there are a few people who see things that lead them to believe that there may be some very small amount of volcanic activity that's still happening on the moon, but nowhere near what it had in the past, and no plate tectonics whatsoever.
And then another question is how, and I don't know if you know the answer to this, but what's the highest peak on the moon?
Oh, that I don't know. I know there's at least one that is 5 kilometers from base to peak, but I don't know if that's the tallest. It's the tallest that I can think of that I know of, but I don't know what the tallest peak on the moon is.
Okay, and then
but it sounds like something that you could probably find out from Google if you gave it a shot. But like I say, all I can say is it's at least 5 kilometers tall, and that's plenty tall for me.
Okay, and then final question, and maybe you'll get into this later, but is there any ice on the moon in any of these craters or in the on the poles? Are there any areas that have ice that we're aware of?
I don't know. My recollection is that there was some indication of ice in some of the craters near the south pole of the moon, but I don't know for sure. It would not surprise me if there were. It would have to be in an area that is almost always in shadow, but that's not impossible on the moon.
Okay.
But I don't know the answer. Okay.
And then we actually had one more that just came in. This is pretty generic, but when you let a kid look through your telescope at the moon, what's the most common question that you get about the moon?
Oh boy. I don't know that there's one most common question. I mean, what mostly happens is they say, "Wow," uh, that's pretty consistent. Probably how far away is it is probably the most frequent question that I get from kids.
Okay, thank you. That's all we have for right now.
All right, let me know if we got more. And in the meantime, let's go back to some of the other kinds of things that we can see on the moon in telescopes. So in addition to what we've talked about so far, there are also valleys on the moon. There's a couple of different kinds, or valleys on the moon happen for a couple of different reasons. In the top left picture, we see it's part of a feature called Valles Alpes, or the Alpine Valley. And it's an area where the rock has basically fallen down between two parallel faults. It's fairly common on the moon. We're going to see when we go through the examples later, we'll see a couple more areas like this. The technical word for them is graben, Graben, and it's one of the things that happens. Also, in the middle of a graben, it's not uncommon to see a rill where the rock that has fallen down gets a split in it down the center, and we can see that in the Alpine Valley graben, certainly. Other valleys on the moon happen sometimes very violently when an impact happens. There are times when the impactor literally just pushes tons and tons of material outward from the crater, and it forms a trough that looks like a valley, and we later identify it as a valley, and we'll see at least one of those in the examples. And the third way that craters form that valleys rather form on the moon is when we have a string of craters that overlap each other, and instead of forming a series of craters like we see at the lower right, series of craters like this where each crater is distinct is called a catena, and those are kind of neat. There's a number of them on the moon, but if you can imagine those craters being closer together and overlapping enough that there was no longer any walls between them, they'd form a trough, and we would label it as a valley, and we'll again see a couple of those in the examples. Now, going back to the lower left, we also can see lava ridges on the moon. All of the mare have lava ridges somewhere on them, and they almost look like waves on the lunar seas. Unfortunately, they're not, because of course they're not seas. What's happening there is one of two things. Either the lava is sitting on top of a raised feature, and that raised feature is causing some disruption in the lava above it. Or what happens more often, and what we see happening here, is another effect of the heaviness of these lunar lavas. In the picture at the lower left, we can see about half of a crater. The reason we can't see the right-hand half of the crater is because it's buried underneath that lava. And the reason it's buried underneath the lava is that the crater must have formed after the basin that the lava filled was there. So it formed on land that was sloping down. And then when the lava filled up the basin, it covered up the low side of the crater, left the higher side exposed. So we've got a bunch of real heavy lava sitting on land that we know is tilted downward, downsloping land, and it kind of tends to shift a little bit, and those little wrinkles happen. One of the reasons that the wrinkles happen is from the shifting of the lava as it sort of tries to slide down that hill. In the center, we have a real delicate feature on the moon. They're very, very difficult to see because they're very small. They're called domes, and they're basically little hills of lava that form around vents where lava used to come out from underground. They're only at most a couple hundred feet tall, and you have to catch them right at sunrise or sunset in order to be able to see them, because as we'll find out in a couple of minutes, we really see things on the moon mostly because of their shadows. So short features like this, only a couple hundred feet tall, don't throw very big shadows, and they don't throw them very long after sunrise or sunset. So we need to look at the right time in order to find them. And then again, we have mountains on the moon. We talked about those a little earlier, that are really not mountains in the sense that we understand them, but just the rim of very large basins or craters. The most important thing to look for on the moon is the terminator. The terminator is not Arnold Schwarzenegger. It's that line down the middle of the moon in the left-hand image where daylight and darkness come together. And that's important because it's just like on Earth. The point where daylight and darkness come together is where sunrise and sunset is happening. And just like on Earth, at sunrise and sunset, the shadows are longest. If you compare the moon on the right with the moon on the left, you're looking at exactly the same moon. All of the features, all of those craters that you see along the terminator in the left-hand image, they're all there in the right-hand image, but you can't see them because the sun is coming from directly above. It's not throwing shadows, and there's very little to define and delineate those craters so you can pick them out. So when you look at the moon, particularly when you look at the moon with a telescope, the place you want to be looking is close to the terminator, where the shadows are long, the features are pronounced, and it's easy to see what you're looking at. At full moon, like on the right, it's very difficult to see anything on the moon in any detail. A couple things to look for along the terminator. It has some interesting effects along the way. One set of effects are called sunrise rays, and you can see a really good example. In fact, this is the original example of a sunrise ray on the moon. The large crater on the left-hand side is a crater called Pitatus, and right around 10 o'clock on Pitatus, there's a small crater called Hesiotis. The sun here is coming from the right side, and you can tell that from the way the shadow falls on that wall on the right side, and how the left side wall of the large crater is lit up. And you can also see there's a little hole or a gap in the left-hand wall of the larger crater, and that little gap allows a little ray of sunshine to come pouring into the smaller crater before the rest of the floor is lit, and it forms a nice little narrow triangle of light shooting across the floor. If it wasn't for that gap in the wall of the large crater, the whole floor of the small crater would be dark. But because of the gap, we're able to see the sunrise ray lighting up the smaller crater. And there's a number of examples of that on the moon, where if you look at the right time, you can see rays of light coming in where really they shouldn't be. They turn up in odd places. The other effects along the terminator are called chiaroscuro, which is just a fancy Italian way of saying dark and light. And the most famous chiaroscuro effect along the terminator is the so-called lunar X, which we can see in these images on the right. As the sun comes up, it lights up the very tops of 3 or 4 different craters. Excuse me. And they just happen to form a nice little X shape that lasts for maybe 3 or 4 hours. As the sun climbs higher, that X will disappear. There's a number of other similar shapes and different letters and numbers and other things that people have found along the terminator at different times of day on the moon. So that's another aspect of lunar observing that you can look for. Finally, before we get to some examples, there's always going to be somebody who thinks that you have to use a filter for the moon, and there's always going to be somebody who thinks you can never use a filter for the moon, and they're both a little bit right. There's good reasons to use filters because it takes the glare off. The moon can be awfully bright, especially if you're looking at it in a fairly large telescope. On the other hand, if what you're worried about is, preserving your night adaptation so you can observe other things, you're going to lose that even with a filter. And the filter prevents moon blindness, where the brightness of the moon literally overwhelms your eye and you see spots. That can happen. Of course, if you have a white light nearby, that will prevent that from happening as well. It's definitely more comfortable to observe with a filter. On the other hand, you do lose some detail. And it's certainly a good idea during public events when people are, maybe not aware of just how bright that moon's going to be. But you can also, if you don't have a filter, you can reduce the brightness by increasing magnification. Normally, you would use a so-called ND or neutral density or gray filter on the moon. Some people use colored filters. I will tell you from experience that if you put a green filter in the moon and tell a 7-year-old that the moon is really green and prove it by showing her the moon through a green filter, she will absolutely tell her teacher all about it the next day, and you'll have some explaining to do. So I don't recommend that. So let's go on to some of the specific things, specific craters we can see on the moon during the course of the month. I'm going to go through these pretty quickly. We have 3 days after full moon. There's a nice flooded floor crater called Endymion up near the top of the moon. Langrenus is a nice detailed set of detailed walls. Petavius gives us a wonderful the so-called 8 o'clock rill in Petavius is very easy to see. There's a valley over to the lower right that's a series of overlapping craters. You can sort of see it just at the edge of the crater there, and that's where those items are found. 4 days after new moon, you have a nice pair of contrasting craters up near the top of the moon, Hercules and Atlas. One flooded, one not. We have Taruntius, which was the flooded floor crater we talked about earlier. And we have paracraters called Messier and Messier A that form a nice double crater with a really interesting ray system going in only one direction, to the lower left there. That's where those are. Next day we have another set of nice rills near Crater Berg. Posidonius, which we talked about earlier, with the rills on the floor, and we have that nice interesting area where the right wall has slumped into what almost looks like a second wall. We have Le Monnier, which is a great example of a crater that formed on the sloping floor of a basin before the lava flowed and then later filled in. We have some nice pair of features either side of a crater called Cauchy on the 5th day, with a set of rimae on the top and a nice scarp or cliff underneath. And Piccolomini, which is a beautiful little crater with some wonderful terracing. And Rupas Altai is, again, it's a little difficult to see here. And that's where those are. 6 days, we have one of my favorites, a pair of craters with a little hoop-shaped piece of terrain to the left that makes them almost look like one of those old little pince-nez eyeglasses. The Serpentine Ridge in Mare Serenitatis is probably the most dramatic lava ridge on the moon. It's a wonderful thing, goes on and on forever. And we have on the 6th a nice trio of craters that you can use for teaching, because we have a young crater, a middle-aged crater, and an old crater in order, right on top of each other, and you can see the features of each. That's where those are. 7 days after full moon, we're right up about first quarter now. We have Valles Alpes, which we talked about earlier, which cuts across the Caucasus Mountains. We have a couple of little mountains there near Valles Alpes, which you can also see on the top, and a great crater called Cassini. If you look at the crater in that middle picture at the lower right, you can see that the lava has filled the crater almost to the rim, and the lava inside the crater is actually considerably higher. I can't remember, 1.2 kilometers higher than the surrounding area, which is pretty neat. It's the way it filled in. We have a wonderful rill called Hyginus that's visible on the 7th day. Also, right at the center of Hyginus, right where the two arms come together, there's a little crater there, which may be the only visible volcanic crater on the face of the moon. It's unusual because it has no rim. It doesn't go up, just down, and it is right along a volcanic feature. So it may very well be a volcanic crater, which would make it the only one that we can see. Day 7, we have another trio of craters that have different characteristics and nice contrast. We have some more nice rills over near Treesnecker, and we have again another trio of this time it's old, middle-aged, and young craters. Day 8, we have crater Plato, which we talked about earlier. One way to test how accurate your telescope is to see how many little craters you can see on the floor of Plato. Eratosthenes, a nice complex crater, 3.5 kilometers deep, which is that's a big swimming pool to dive into. And our friend the railway or Huygens sword over there on the right, again showing us the nice details along the cliff. Day 9, again another nice complex crater. This has some nice radiating ridges coming out from the crater itself, where debris was strewed around the outside of the crater. Copernicus in the center is truly magnificent. It's one of the youngest craters on the moon, and therefore one of the most detailed, where you can see just all sorts of remarkable things going on. And Clavius, which is down near the bottom of the moon. Those of you who are fans of 2001 will remember Clavius Base, and even if you're not, you have to appreciate, I think, that nice little arc of subsequent craters that covers the floor of Clavius, getting smaller and smaller as it goes along. I think that's a wonderful feature. Still on day 9, more gorgeous detailing in crater Borealis, and there's a nice little, if you look over to the left of the crater, you can see a little valley heading up to the northwest in a little rectangular area. Looks like a bridge going across a country stream. It's a very nice feature. Our friends Pitatus and Hesiotis, where we saw the sunrise ray, but more importantly, in this view, just to the lower left of the small crater, we can see a crater called Hesiotis A, which is a so-called concentric double crater. It's not 2 impacts, and again, this is something those of you who would like to have one of those Nobel Prizes, good question for you is, how does this happen? There are several of them on the moon where there are almost perfectly concentric double rings, and it's not at all clear how exactly they came about. Day 10, we have some domes, very subtle again. As you can see, this is probably a little past the point when they would have been most visible. They're starting to get a little difficult to see here. Hippolus rills, which is again an easily seen set of rills. Crater called Heinzel, which is actually 3 separate impacts that happened at different times in almost the same place, and it always sort of looks like an open walnut, or maybe somebody made a peace sign or a Mercedes logo on the moon. Some more domes on the 11th. We have the crater Gassendi, one of several diamond ring type craters where we have a large crater with a smaller crater perched up on the top like the diamond in a ring. And we have crater Schiller, which is a neat crater. It's a little unclear whether it was a very angled impact that sort of made a trough rather than a traditional crater, or whether it was an impactor that broke up as it was coming in and made that trough through several impacts. And then finally, I think this is the last of them on the 12th day. Wonderful area around Aristarchus, which is that bright crater that we saw way back at the beginning, in the top left corner of the full moon. It's on a diamond-shaped plateau that is again somewhat puzzling. It's You can see the diamond shape pretty well in this image. It tends to have a strange, almost mustard kind of color to it. Not sure exactly why. We have crater Reiner, and you can see Reiner Gamma, that white swirly feature with the magnetic anomaly underneath it that we talked about at the beginning, and a couple of craters near the lower left corner of the moon, one of which, the one that the red arrow is pointing to, is again another crater where the lava that flowed into the crater is taller than the surrounding surface, like in Cassini that we saw earlier. How do you find your way around the moon? Well, Orion's Moon Map 260 is a very good choice. Costs $13. It's nice because it has both correct image and mirror reversed views. If you're looking at the moon in a refracting telescope, you're going to need that mirror reversed version, because otherwise you will be nothing but confused trying to find your way around. Sky and Telescope also sells some good moon maps, and there are others as well. But Orion and Sky and Telescope are the ones that I would recommend most. Or you can get some freeware called Virtual Moon Atlas, which will allow you to basically make your own moon maps. It's fairly intuitive and worth looking up. Now, just going to take a couple of minutes about observing a lunar eclipse, because lunar eclipses are kind of neat. So again, for an eclipse to happen, we have to have the sun, the earth, and the moon all lined up, and we know the moon has to be at a node. It can't be above or below the plane of the earth and the sun. And this is how it lines up. You can see there's the dark shadow of the earth called the umbra, and that's where we want the moon to be for a decent eclipse. When the moon is in Earth's penumbra, which is the lighter shadow of the earth, it's literally impossible to tell by eye that an eclipse is going on. The only way to really prove that it's going on is to use photographic measurements that are much more sensitive than your eye. You will not be able to detect a penumbral eclipse by eye alone. What happens is the moon starts moving into Earth's umbra. You can see the shadow of the Earth starting there at the bottom right end of this string of moons. You can see it's starting to come up a little more, comes up a little more, and then right about the point where the Earth's shadow completely engulfs the moon, something really remarkable happens. It turns red, and sometimes it turns a little red, sometimes it turns blood red, sometimes it turns a copper so deep that you can barely see it. But that's almost all lunar eclipses involve a distinct reddening, and that's why lunar eclipses are sometimes referred to as the blood moon. We're going to talk in a minute about why that happens, but first take a moment on how you grade or scientifically describe a lunar eclipse. There was a scale that was developed by a French astronomer named Danjon in 100 years ago right now. Basically just grades them according to how deep the red color is, and it ranges all the way from very bright coppery red to very, very dark eclipses. So where does that red color come from? Well, if you look at where the sunlight's coming from, you can see that the sun barely scrapes the top and the bottom of the earth as it comes by, forming the shadow. Now, when sunlight comes through our atmosphere, it bends a little bit. Not a lot, but just a little. Bends in just a tiny bit. And the place where the sunlight is touching our atmosphere is right along Earth's terminator, that line between the lit side of the Earth and the dark side of the Earth. And what do we know about the terminator? Well, the terminator on Earth, just like on the moon, the terminator is where sunrise and sunset are happening. So as a lunar eclipse is going on, the moon moves into Earth's shadow, and there's a little bit of sunlight that comes through the atmosphere right at the points where sunrise and sunset are happening, and that sunlight bends in just a little bit, just enough to light up the moon. And what happens is the moon takes on the color of all of the sunrises and sunsets that are happening on Earth at that moment. They're refracted onto the face of the moon, and that is pretty cool. So that's what I know, and if we have any other questions, I'd be happy to try to answer them.
We do. We have one person who doesn't seem to care much for the moon when it comes to observing, and he asks how many days on either side of new moon can he expect to not be hindered by the moon when he's trying to look at DSOs, deep sky objects.
It's not that easy, because part of it depends on time of day. What you want to do if you're, I don't have as much aggravation between third quarter and new as I do between new and first quarter. Now, there may be people who feel differently, but don't forget third quarter to new. It's coming up earlier and earlier, but it still doesn't come up until the morning. So you get some decent time in there. Generally, I think you should be able to get a total of a week is not unreasonable to plan for.
Okay, and then the only other question, you kind of answered this earlier, but do you know when it comes to moon maps, say you had a Dobsonian or a Schmidt-Cassegrain, do you know the different orientations of the map that you would need for those? You already mentioned a refractor would need a mirror image, right?
Right. The others are easy. The only one that's difficult is the refractor, because it's that left-right mirror image. For Dobsonians or for any other reflecting telescope, or for Schmidt-Cassegrains, all you have to do is turn the map upside down, because it's what you're seeing in the telescope is upside down and backwards from reality. So if you turn the map upside down, you should be seeing what you're seeing in the telescope.
Okay, I think that is all the questions. I did look up that Mons Huygens is 6,500 meters tall on the far side of the moon, and then
Okay.
Scientists have found ice on the moon, and actually they say all over the moon in tiny little craters. There's spots that don't get sunlight, and they think that those all have ice in it.
Right.
We just had one more come in. While the moon is not known for having an actual atmosphere, I heard it has a minuscule amount of various gases mixed within its loose surface. Where does that come from? Are you qualified to answer that question, Rick?
I'm trying to recall, because I recall reading the same thing, and I think, I mean, I could be wrong, but I think it's basically off-gassing from chemistry that's happening underneath the regolith. So in other words, I think that gas is coming upwards, from the moon, but I'm not at all positive because it's something I read a while ago. I mean,
and then the gravity kind of holding
it doesn't affect observing the moon, so it's not something I worry about too much. Because I'm not planning to visit there.
You didn't get your ticket for.
Well, I thought that Branson. I just assumed that Branson was going to take me along, but
Yeah.
So.
Okay, well, I don't see any more questions. Rick, thank you very much.
All righty.
And
everybody have fun out there.
We will let you go. Appreciate it. Thank you, Rick. Thank you, everybody,
Okay.
for watching.
Good night.